Good evening, everybody, and welcome to today's session under Curious Mind series by Propagation Institute of Space and Technology. Like you, majority of the people who have attended previously, you already know that this is an institution dedicated to space science education for both schools and college students. And before we begin, I would like to mention that first that Sir will deliver this session, followed by an interactive discussion segment where participants can directly ask their questions by turning on their mic and camera. Okay. Now, today's session is titled Hyper Relativity, Exploring Relativity and Creation. We are very honored to have with us today Mr. Hiten Shelar, an astrophysicist, a science communicator, and a best-selling author. He's known for his work in astrophysics communication and for authoring multiple books on astrophysics and cosmology, including his recent book, Hyper Relativity, which is gaining international recognition through Hyper Relativity World Tour 2025-2026. And on behalf of the entire propagation team, I warmly welcome Mr. Hiten Shelar and all the participants joining us today. So thank you for being with us. I would like now to hand over the mic to you, and you can begin the session today.
Thank you for kind introduction, and I'm really glad to be here. Dealing my session on hyper relativity at Propagation Institute, and so space lovers, universe lovers who actually wanna love who actually love to know about the universe. You're gonna like this session, okay? So we go across the university around the world, and this is the favorite session of mine, of everybody. This is the hyper relativity session, all right? So, wanted to just ask you guys, anybody of you ever watched the movie Interstellar? Interstellar, anybody of you? Just you can raise your hand, maybe. Just give a thumbs up like that. Interstellar. So this lecture, yeah, so there are a lot of thumbs up right there. Wow, amazing. That's really amazing. We have a lot of soft thumbs up. So if you like the movie Interstellar, so you are gonna love this lecture because it is all about the relativity. It's all about relativity. What the essence of relativity? What is time? What is space? And how it's linked to the creation itself. So it is all about that. And so you're gonna love it, right? So without any delay, I think we should start with the lecture. Okay. So I would be sharing a slide with you. Okay, I will share with the screen with you, right? So. Are you guys able to see the screen, by the way? I hope so you are able to see the screen, right?
Yes.
It's perfect. So we would be exploring the hyper relativity, all right? Which is our universe is just relativity in hyperspace. So we'll be looking at for that. But we across this lecture, we'll be dealing with topics like relativity, speed of light, and black holes, all right? So it's gonna be a lot of fun. So guys, before going to the hyper relativity and relativity itself, I want to introduce you guys to something called the hyperspace. Okay, so hyperspace in dimensions. Okay, so hyperspace is random number of dimensions, guys, like from ranging from 0 to infinity. Okay, so if you guys actually know about the dimensions, let me show you just a second. So we have like 0 dimensions, for example. Look at the screen, guys. So this is 0 dimension, okay? Just a single point, which has no dimension at all. All right, this is 0 dimensional. Now we have 2 such 0 dimension. Now we extend it in a higher dimension, okay? And what we have is 1 dimension. We have like line, all right? A line,
Sir,
which is a dimension.
slides are not changing, sir.
I'm not changing the slide. I'm actually drawing on it.
Okay.
So is my drawing visible in the lecture?
No, sir, it's not visible.
It's not visible?
Yes.
Just a sec. Let me share the screen again. All right, you can just see right here. So let's say we have a point, okay? Like a 0 dimensional point, all right? Which has no length. And now we have 2 such points, all right? And when we connect 2 such points, we get a line, a straight line, a dimension, okay? Now we have, which we call a 1 dimension, okay, guys? Now we have 2 such lines like this. And now when we connect them in a higher plane, what we get? We get a square, okay? Now that's what we call with 2 dimensions, guys, all right? So now we have two such squares, and we now extend them in a higher dimension. Now we extend them in a higher dimension. What do we get? We get a cube. Perfect. Now, so I will be sharing my screen right now. So because now what we are going to deal with is something we need to picture. We actually have to see through our eyes, like what is it, you know? So I hope so my screen is visible right now. Is it?
Yes, sir, it's visible.
All right. So yeah, perfect. So, okay. So as I said, so we have two such planes and we extend them in a higher dimension. So what we get is a cube. All right. This is a three-dimensional. But now when we have two such cubes, okay, two such cubes, and now we actually extend them in a in one dimension higher still, in 4 dimensions. All right. We get something called a tesseract. Yes, we get something called a tesseract. Now, of course, this is a relativity lecture. What I'm talking about dimensions, you will get it very soon, like why I'm dealing with that. So a tesseract is a high dimensional cube, guys. It's a 4-dimensional cube. It's a hypercube. It's also called a hypercube as well. So it's a tesseract is a high dimensional cube. Okay. So what I'm going to show in the next slide is a tesseract, is the shadow of a tesseract. Okay. It's a projection. It's a 4-dimensional cube, guys. Like as I explained, like a 3-dimensional cube. Now, when we have a 4-dimensional cube, is a tesseract. Okay. So what I'm going to show you in the next slide is a shadow of a tesseract. And the shadow itself looks so damn bizarre. The shadow itself, in the next slide, I'm going to show you the shadow of a tesseract, and the projection of that tesseract itself looks so damn bizarre. And now you see, then you imagine that how the original tesseract, how bizarre it will actually look. Okay, so here is just the shadow, how the shadow of the tesseract looks like, which is the projection of a tesseract. Okay, so just a second, we get here. So this basically is a shadow of a tesseract. Okay, so we are not able to see actually the screen. Just a second. Okay, perfect. Is my screen moving?
It's still now, but just make any
Not
changes.
moving, sir. Try making it full screen, and that might move it.
Just share the whole screen, sir. Then everything is gonna work properly.
Okay, so from actually I did it full screen, right?
Yeah,
Yeah,
it's happening.
yeah, it happened a little bit. So this right here, what we call a tesseract, and it's just a shadow of a tesseract, guys. Okay, this is the only animation in this slide, so don't worry about it. We can deal with all the slides. So this is just a shadow of a tesseract. Okay, and the shadow itself looks so damn bizarre. The shadow itself looks so damn bizarre. So guys, imagine how original tesseract would look like. Okay, how original tesseract would look like. So why I'm teaching you guys tesseract, okay? Why I'm even doing that? Because our universe, all right, is as bizarre as this tesseract. Get it? Our universe, the space-time universe, is a 4-dimensional thing. Okay? It's just not like asking like questions, random number of questions in a 3D world or something. So we are actually asking the questions about a 4D world, which our universe is. This is the 4-dimensional tesseract, guys, and it itself looks so damn bizarre. It itself looks so damn bizarre. Okay, so our universe similarly is a 4-dimensional thing. So it really matters. So we are in hyperrelativity. We treat our universe not just as space, but space-time, a hyperrelativity thing, a hyperspace thing. Okay, a 4-dimensional entity, the space-time, and it changes a lot. For example, let me give an example, guys. Okay, for example, it's very natural for us to ask the questions like, where is the center of the universe? We generally ask this question, right? Like, where is the center of the universe? In the normal, it's very normal for us to ask the question. But you know what? This question is very wrong because it forgets about time. All right. For example, when you let's say you have a train tomorrow, then the first question you ask is, on what platform is my train arriving? So you ask a location in space. All right. And the second question you ask is, at what time? Right? So you need a location in space and a location in time. All right. So our universe is space-time thing. So any point on this space-time is also its location plus its time. Its location plus its time. So it's not just a location. So stop asking where is the center of the universe. Instead, ask what event is the center of the universe. Because any point on the space-time is not just a point in space. It's not just a point in time. It is both. It is point in space as well as it is point in time. It is basically an event, guys. Okay, it is basically an event. So instead, ask what event is the center of the universe instead of asking where is the center of the universe. So the center of the universe is an event, guys. All right, and so it actually changes our way of asking the questions. Okay, so that's the power of actually treating our universe as a space-time thing. So, and yeah, so and hyperspace is, guys, four-dimensional. For those who have been like very new to the Tesseract, it is very bizarre, guys. Let me explain it in form of a story, or maybe like, say, let's say a guy named Joe gifted a house to his parents, let's say in Mumbai. Okay, so a house has like it's like a 5-story building, and each of the floor of the house has a room in it. Okay, and a ladder going up. All right. So when and so what happens in Mumbai? Suddenly an earthquake comes. Okay, suddenly an earthquake comes, and all those floors actually they start to topple over each other. They start to topple over each other. Okay. Now in the story, what happens is that all those floors go into the extra dimensions. Just hear me closely, okay? Bear with me. So now those guys actually went to check what happened with the building and what happened with the room. So Joe entered the first room. It was in Mumbai. It was all right. But when he tried to enter the second room, okay, and he opened the second room, he finds himself in Paris. Are you like what I'm saying? Bear with me, all right? He opens the third room, maybe. He finds himself on the moon. Thank God the windows were closed, because there's like a vacuum out there. There's a vacuum out there. Exactly. I mean, yeah, it sounds bizarre, but bear with me, okay? He goes into the third room now, okay? And he finds himself on maybe Mars or something. He goes in the fourth or fifth room, and he finds himself maybe in New York. So what exactly happened here, guys? So when the earthquake came, all those rooms actually, instead of collapsing into the 3D world, those actually went into a higher dimension. What the reason behind telling the story was, I just want to give you a picture of a 4-dimension, like how it feel like for those who are very new to this. Okay, so this is how bizarre the 4-dimensional world is. You can travel anywhere without physically traveling in the 3D world. You can go to the, let's say, to the opposite side of the earth without actually traversing that distance. Okay, so that's the power of the 4D world. So this is how bizarre it is. And the main thing is that, what is the main thing? The main thing is that our universe is as bizarre as this 4D world. So we have to take this into account, that our universe is as bizarre as this 4D world. All right. So this is about the higher dimensions. So hyperspace, as I said, it ranges from 0 to infinite number of dimensions. But our universe, okay, is a space-time universe. If you know, our universe is a space-time universe. It has 3 dimensions of space, and it has 1 dimension of time. 3 dimensions of space, and then 1 dimension of time. So it has this 4-dimensional universe. All right. So our universe is basically a 4-dimensional universe. So it is as bizarre as this thing. Now, but what makes, you know what, guys, Einstein said that time is just same as space. Okay, time is just same as space. So what made this space plus time different from the hyperspace? If hyperspace was existing like from 0 to infinity, why only these 4 dimensions of the universe, the space-time universe? Why are only this space-time? Why is this space-time special from the hyperspace? And now here comes the part of the relativity, guys. Today in the hyper relativity lecture, we're gonna learn about the essence of relativity itself. what relativity exactly all about. Okay, so we are going to learn in this lecture. Okay, so I want you to hear this closely, guys. All right, hear this closely. The faster you move in space, the slower you move in time. And the faster you move in time, the slower you move in space. Okay, you got it? The faster you move in space, the slower you move in time. And the faster you move in time, the slower you move in space. This is the very important thing you guys have to remember for this lecture today. You're gonna love this lecture. Like, you're gonna learn the like very basic relativity, what relativity is all about. You're gonna get the essence of relativity. Guys, who doesn't like relativity? Relativity is really amazing. Okay, so take this note, guys. The faster you move in space, the slower you move in time. And the faster you move in time is and slower you go in space. So this is how it works. But so this is kind of, guys, like a tug of war. Okay, a tug of war happening between space and time. All right, so the faster you move in space, the slower you move. Let's say the faster you move in space, the slower you move in time, and the faster you move in time, the slower you get in space. So it's like a tug of war, and this tug of war happens in no dimensions of hyperspace. This tug of war happens in no dimensions of hyperspace, or this happens only with the first three and the fourth dimension. So this tug of war between the first three and the fourth dimension is what makes this space-time, is what makes the space-time different from the hyperspace. Okay, we see none of this tug of war in any other dimensions of hyperspace, and this is what makes space-time special from the hyperspace. So what I told you guys, that the faster you move in space, the slower you move in time, and the faster you move in time, the slower you move in space. This is what relativity all about. This is the essence of relativity. Relativity is all about this. I in fact call it relativity itself. This is what relativity all about. Okay, so whenever we have this tug of war in hyperspace, you do create the universe. So I hope so you guys can actually you are actually able to see the slide. So yeah, perfect right there. So how space-time differs from the hyperspace? It's written here: the faster we travel in space, the slower we travel in time, and the faster we travel in time, the slower we travel in space. So this tug of war always happens. Okay, but in tug of war, we pull the rope, guys. Okay, on either side, either this side or this side. So what are we pulling exactly? Even if it's tug of, what are we pulling exactly? It's nothing, bear with me, it's nothing but the speed of causality. Okay, so there is a definite speed called c, which you also call the speed of causality. I will show you its value. Okay, so it's the speed of causality, it's the definite speed. So either you pull it in space. If you pull it in space, you start moving in space, and if you pull it in time, you start moving in time. All right, so this speed of causality c, this speed of causality, or I just mentioned c, is it's something which we always move at, either in space, either in time. And you wonder what the speed of causality even is. The c is nothing but the speed of light. Guys, you know what? We always move in speed of light, either in space, either in time, or partially somewhere in both. For example, what I said, it's always the tug of war. The faster we travel in space, the slower we travel in time, and the faster we travel in time, and the slower we travel in space. So once we have the entire c in space side, we have nothing left on time side. So space wins the tug of war. So light travels at speed of light in space. This is the reason why. This is the reason why light feels no time at all. Light feels no time at all, guys, because it has the entire c on its space side. And on other hand, we are resting here in space. So what does it mean? It means that space side has lost the tug of war, and so we are actually traveling at speed of light in the dimension of time. So at the end of the day, we all are moving at speed of light, either in space or either in time, or maybe sometime like partially both. But at the end of the day, as totality in space time, we all are moving at the speed of light. In space time, in four-dimensional space time, we all are moving at speed of light. That's the truth. Okay, so we have to get this into account. And yeah, so this is all about the tug of war. But guys, who is exactly playing the tug of war? Ever wondered who is exactly playing the tug of war? For example, for a tug of war, we need a rope. For a tug of war, we need the players. So who are the players here? Who is actually playing this tug of war? It's nothing but matter energy. Matter energy play this tug of war. And this tug of war is all about the speed of light. Either you get the speed of light on the space side, or either you get the speed of light on time side. If you get it on space side, it's like light. Light only travels at speed of light in space. It doesn't feel any time. And if you get it on entirely on time side, it's like us. We are resting here in space, but traveling at speed of light in time. All right. So in totality, we all travel at speed of light in space time. That's the thing. And the players, who are the players here? As I said, it's nothing but the matter energy. The matter energy are the players of this game, right? The matter energy are the players. So matter energy, okay? And also for matter energy, we need space time to exist. But for space time to exist, as I said, we need the relativity. We need the relativity, as I said, guys. It's all about the faster we travel in space, the slower we travel in time, and the faster we travel in time, the slower we travel in space. So we need matter energy, we need we need space time, we need relativity. All these three things, like namely matter energy, space time, and relativity. These three things coexist. And wherever these three things coexist, there is the universe. Relativity is just, universe is just relativity in hyperspace. But relativity needs the players, which is matter energy. And we also need relativity, of course. And we need space-time for matter energy as well. So these three things actually do coexist. So matter energy, relativity, and speed of light. These three things do coexist, guys. So as it is written very well right here. Space-time, matter, energy, and relativity. So all these three things coexist. Where there is relativity, there is the universe. As I said, space-time, matter, energy coexist. The creation of space-time is the beginning of relativity. The universe, as I said, is just the relativity in hyperspace. Guys, you should understand the essence of relativity. Okay, so it's relativity is all about the faster you move in space, the slower you move in time, and the faster you move in time, the slower you move in space. Okay, and this is the essence of relativity. Once this is the first thing you should remember, you should understand. Once you understand this, you have cracked the relativity. Okay, relativity of all kind, maybe the special theory of relativity, or may it be the general theory of relativity, it is all about this. It is all about this. Okay, so space time, matter energy, and relativity, all these three things do coexist. All right, and wherever we have the existence of these three things in hyperspace, we have the universe. Okay, now guys, I hope so it's very clear. Okay, so remember this, the faster we try, again I'm saying it on repeated basis, guys, because it is very important. And after this, I'm going to tell you a second important thing, and it's really amazing, guys. Okay, ahead as we go in this lecture, this is going to be like very, very, very interesting. Starting from the basic, it's gonna hike, the interest level is gonna hike up exponentially. Okay, so once more time, please. Okay, bear with me. The faster you move in space, the slower you move in time. And the faster you move in time, the slower you move in space. And this is all about the relativity. This is the essence of relativity. All right. So now let's talk about the infinity, guys. Okay, infinity. So many people like the infinities. Some mathematicians are scared of the infinities. Like they don't like infinities at all. So, but when this infinity comes in the form of this in the form of a speed, okay, when the infinity comes in the form of a speed, we get the infinite speed. And do you wonder what is the infinite speed? What is the infinite speed of the universe? We know the fastest speed of the universe, but the fastest speed of the universe is also the infinite speed of the universe, okay? And related, the second point to crack this is the infinite speed of the universe, guys. This is actually the infinite speed of the universe. And once you cracked it, once you realize it, that the speed of light is the infinite speed of the universe. This is the second thing to realize, guys. You have cracked it. In relativity, we practically, theoretically, we mathematically as well, we treat this number as the infinity of speeds. Of course, it looks like a definite number, okay? But this number is all about this number is infinite speed, and the space-time makes sure, the fabric of space-time makes sure that this number stays infinity. This number stays infinite all the time. So maybe we have learned about time dilation, length, contraction, effects of relativity. It is just to keep this number infinite. Okay, so this number is the infinite speed of the universe. And once you realize it, is the second thing to crack the relativity. Okay. Now, this is the infinite speed of this. So this is the second thing to remember, guys. Okay. Now, next question you guys might ask, okay, if this is the infinite speed of the universe, then why does light take, if light travels at the same infinite speed, then why does light take 8 minutes to cover the distance between sun to the earth? Ever thought about that? If this is the infinite speed of the universe, and light also, if you say, doesn't take any time, if you ask the light, since light travels at the speed of light in space, it feels no time. So if we actually ask the light, like knock light, how much time is required to cover that distance between the sun to the earth, light will say no time at all. So why does it take 8 minutes, guys? Why does it take 8 minutes? Why does it take 8 minutes for light to cover the distance between the sun to the earth? Ever thought about that? I give you 30 seconds, just think about it. We might cover the comments, like, in the comment section. I'll give you just 30 seconds. So think about it. Isn't it a great question? Why does it take 8 minutes if light feels no time at all? So I'm going to reveal it. Why does that happen? All right, perfect. So in space-time, guys, we deal with a very basic thing called the Minkowski space-time diagram. Actually, I'm not able to show the slideshow here on the screen. Why? I'm not able to understand that. Why? But actually, I wanted to draw. But okay, if you guys actually can see the cursor, then please, we can actually represent it. I mean, it would be better if we have a marker pen or something, but I think we don't. Fine, sure. You guys can focus at the cursor. Okay, so I will name the points right here. Perfect. Okay. So why does light know its observer before the observation? That's the question. Because since for light it takes no time to cover the distance between the sun to the earth, so light always knew whose eye it was going to enter into even before we watch. It feels like that, right? So what's exactly happening here, guys? Does light really know before its observation? So let's go with that. So let's see if it still can happen, because I think no, we can't actually do it, or maybe we can. I think show on my screen anyway. Just a second. Okay, perfect. We can draw. All right. So I hope so. You guys can actually see me drawing.
Yeah, sir, it's visible now.
Yeah, it's visible right now. Okay, so on the screen, if we actually see, this is in Minkowskian space-time. I will give a short description of a Minkowskian space-time diagram. So it's like a Google Maps, guys. Okay, it's like a Google Maps where the Herman Minkowski, yes, someone said right, Herman Minkowski. So in this diagram, we actually have the line, or let's say on a Google line, we have our like maybe like our the line we have covered or the distance we have traveled. So when we map the path of light in the Minkowskian space-time diagram, we do in the form as like a 45-degree line, like this 45-degree line right here. All right, this is the only thing, and this is space-time diagram. Okay, the same distance-time diagram which we have might have learned in school or college, but we have some it has been set like to the relativity, to the equations of relativity. And in this, just we have to remember one thing, that speed of light travels at 45-degree angle here. All right, and we just travel straight, and we can never travel at 45-degree angle because nothing can travel at the speed of light. Okay, so we have to make that sure. We have to make that sure that uh, we have to remember that. I'm sorry, that we have to remember that light always travel 45-degree angle here. Now let's know, why does it take 8 minutes for light to cover the distance between sun to the earth? Okay, so this W is our world line, guys. Okay, our world line. And since, as I said, we are traveling at speed of light in time, for those who just missed it, again, I'm saying the faster you travel in space, the slower you travel in time, and the faster you travel in time, the slower you travel in space. So all about that tug of war. Okay, so light travels at speed of light in space, but rests in time. But it is opposite in our case. Okay, we rest in space, but we travel at speed of light in time. Okay, so in this diagram, we all are traveling at the speed of light in the time dimension, and light is like omnipresent, it's already present. So I have like shown like in form of a dotted lines. If you actually see this dotted line right here, so I have been presenting here in form of this dotted lines. Like this is our world line, we going ahead, and this P1, P2 and P3 are just the flashes of light. All right, these are the flashes of light, P1, P2 and P3. So I have shown them in a solid line because light, for light, time doesn't exist. Okay, so it is traveling at the also it is traveling at the infinite speed of the universe, as I just explained in the previous slide. Okay, so I have shown like a solid dotted line right here. Okay, now we are traveling at speed of light in time, light is traveling at speed of light in space. Okay, so every time we intersect this light here, we intersect this light here and this right here after 8 minutes. Getting it? Light is already there. Light takes no time to reach anywhere in the universe because time doesn't exist for light. But it is instead us who are interacting P1, we're interacting P2, and we're interacting P3 after 8 minutes. Look, understand, guys, we are experiencing this universe. We are experiencing this universe at a pace at which we are traveling in time. Every experience, every motion we perceive, every form of a thing we perceive in this universe is at a pace at which we are moving in the dimension of a time. And at what pace are we moving in the dimension of a time? At what speed are we moving in the dimension of a time? It's the speed of light. So everything we encounter in this universe, we encounter at the speed of light. So light has no component in time direction. It always travels at c in space. So, but it is instead us who are meeting the P1, P2 and P3 after 8 minutes. You get it? What is the general notion? That light takes 8 minutes for us to light takes 8 minutes to cover the distance between the sun to the earth. But no, light is traveling at the infinite speed. Light takes no time to reach from sun to the earth. It is instead us who are intersecting P1, P2 and P3 after 8 minutes. So it is instead us. This is the difference of picturing this universe at 4D level and a 3D level. Okay, and this is the original picture. So it is instead us who are traveling and who are meeting light after 8 minutes. Okay, that's the thing. So yeah, perfect. So it is instead us. Light takes no time at all. So it is instead us who are taking 8 minutes to reach the light. Okay. So since we are traveling at speed of light, see, it is instead us. We are taking 8 minutes in time. All right. That's how it works. Now, guys, there's one more thing I would like to see here in the comments section. Like there's one more thing that travels at speed of light, like light. There's one more particle. What that particle is? Can you guess, guys? Please mention in the comment section if you can. Yeah. No, neutrino. Oh yeah, neutrino. I don't think neutrino travels at this. Neutrino has a very tiny mass, guy. It's not massless. Higgs boson is, of course, it travels at the speed of light. Higgs boson always, of course, it travels at the speed of light, but it's what do you say? In physics, we actually don't. It's like a kind of a quasi particle. It's not. We don't treat Higgs boson. It's like a quasi particle. You get it? No. So somebody said gravitational waves. Someone said the gravitational waves. So it's a graviton. All right. The quantum mechanical analog of gravitational waves. Exactly. So Dhanvin says graviton. All right, that's really correct. Graviton travels at the speed of light. Okay, so the same thing. Look at the slide, guys. So the same thing, but we have like here P1, P2, and P3. But in the next diagram, what we're gonna have is the just a second. Let me clear all, maybe I'll just stop annotating. Okay, here we go. And you can actually see this. You can just a second. Of course, graviton is a hypothetical particle, guys, but you know what? We do have the original gravitational waves in the picture, so it's not as hypothetical as you might claim it to be. Okay, so the same diagram like which we saw before, but instead we have like G1, G2, and G3 right here. Okay, so we have G1, we have G2, and we have G3, guys. All right, the same diagram like before. The same diagram like before, but instead we just have G1, G2, and G3. Now just, yeah, perfect. So what's the takeaway from here? What's the takeaway from here? Why just I'm mentioning this diagram after this? You wonder why? Because what I really want to show you guys is that like light, we are also interacting with G1, G2, and G3 after 8 minutes. Like for example, we are experiencing the gravity at the speed of light, just like we are experiencing this world at the speed of light. Okay, for example, in the last slide I just showed you guys, that it is instead us who are interacting with P1, P2, and P3 after 8 minutes. We are interacting with the sunlight after, it is us who are interacting with the sunlight after 8 minutes, not the light. Similarly, it is instead us who are interacting with G1, G2, and G3 gravitons at the speed of light. Now, this is just a non-continuous source, guys. This is the non-continuous source of gravity. That's why it's called gravitational waves. But it is also true for gravity in general. So we are experiencing the gravity at the speed of light. We are interacting with the gravity at the speed of light, because we always travel at speed of light in the dimension of time. Perfect. So we always interact with gravity, G1, G2, and G3 with at the speed of light. We always interact at the speed of light, basically. Yeah. So we interact with photons at the speed of light. We interact with the gravitons at the speed of light. Okay. Perfect. Now, these were like G1, G2, and G3. These were the non-continuous source, guys. These were the non-continuous source of gravity. For example, this flashlight in my phone. All right. Now, this is This is the continuous source. This is the continuous source of light. But now when I get P1, P2, P3, you get it? So similarly, we have G1, G2, and G3. But what about the continuous source of gravity, guys? How does the continuous source of gravity look like? This is G1, G2, and G3. And again, this is P1, P2, and P3. But how does a continuous source of gravity looks like, just like this continuous source of light? How does the continuous source of gravity look like? You want to say it? Okay, first, let me clear it, the diagram all. And this is how, guys, the continuous source of gravity look like. This is how the continuous source of gravity looks like. Okay, exactly. So just like this is the continuous source of light, and we get P1, P2, and P3. This is the continuous source of light. And when we just create some hindrance in this continuous source, we get G1, G2, and G3 as the gravitational waves, or we call maybe the graviton. All right. So this is the continuous source of gravity, and it is created by Earth. It is also called the space-time curvature. So the takeaway from this is that what we learned that, and this same space-time curvature is what we experience as the gravity, guys, as the gravity itself. Many people must be knowing about it, but in hyper relativity, you get a totally different picture of gravity itself. Okay, so it's just the same thing, guys. So in previous slide, we learned about this G1, G2, and G3. Okay, so but when the time gap between the G1, G2, and G3 goes to 0, when this time gap between the G1, G2, and G3 goes to 0, we get this continuous source of gravity. We get this continuous source of gravity. It's all about it. Okay, so this thing is all about the continuous source of gravity, and we are in it basically. Okay, but you wonder, like, for example, I have this continuous source of light. Now this is what I do to create P1, P2, and P3. But if I want to create the gravitational waves from it, what do I do? So imagine this is a neutron star, guys, and we have two such neutron stars. All right, we have two such neutron stars. I'm not able to show the extended slideshow. I don't know why, but this was actually the animation. But all right, you might get the picture. So when these two neutron stars are like on a look at my hands, okay, are on head-on collision with each other. Okay, they create like ripple around they create a ripple in the space-time when two continuous source of gravity like are on head-on collision with each other. Try like take a rubber sheet and try throwing the marbles on it. First they will go around each other. So similarly the same thing is happening. Two space-time curvatures are going around each other and they are creating these wiggles. So they are creating this P1, P2, and P3 in case this is G1, G2, and G3. So this is how a gravitational wave created. Okay, this is how a gravitational wave created, guys. Okay, so ahead in this lecture, guys, we will be doing we will be getting at a very interesting part about relativity, about hyper relativity, guys. Okay, so bear with me, just bear with me. Okay, and you're gonna enjoy the process itself as well. All right, so this is about gravitational waves. So very interesting question I'm really gonna ask you, okay, in the next is that just see. So next slide, do you guys know LIGO? Just raise your hand if you do. Do you guys know LIGO? Yeah, so many people have like raised their hands. Yeah, LIGO. So it's a laser interferometry observatory at Geneva, Switzerland. The laser interferometry gravitational wave observatory at Geneva, Switzerland. So it has that L-shaped arms. I'm going to ask a very, very, very interesting question, guys, this time. Okay, so this L-shaped arm which it has. Okay, now when a gravitation, it measures the gravitational waves. So when a gravitational wave pass through these L-shaped arms, one of the L-shaped arm, whenever gravity passes through this thing, for example, gravitational wave passes through this book, let's say, okay? Now, when the peak passes through when the gravitational wave peak, the peak of the wave passes, it will get like this. It will squeeze, okay? And when the throw of the wave passes, it stretches. It stretch and squeeze, stretch, squeeze, stretch, squeeze. This happens whenever gravitational wave passes. Stretch, squeeze, stretch, squeeze, stretch, squeeze, stretch. This thing happens. Similar thing happened with these legs of the L-shaped arms of the LIGO. And here at this center, we have the laser. Okay. And when one of these arms right here, they shrink in size due to the squeezing and stretching effect of the gravity, these two light beams, which were actually canceling each other, they failed to cancel, and we actually see the light. We actually see the light on the detectors, and we point our telescopes at that point and okay, there's the neutron star, two neutron stars colliding. But then now the very interesting question I wanted to ask you guys is that everything needs energy, guys, right? Everything needs energy. If I want to drive a car, I have to put like fuel in it, right? If I want to drive an airplane, I have to put some fuel in it. But the energy, what is the source of energy of pulling of these L-shaped arms? When we pull them, it requires energy, right? We squeeze and stretch them. What is the source of energy? Any guesses? Can we guys mention in the comment section? What is the source of energy? Like this, of course, it is the gravitational waves, but what is the original source? Any guesses? It's very interesting, guys. Very, very interesting. And that's one of the things I love about gravitational waves. Wow. Mr. Naveen Kumar says the neutron stars. That's really amazing. And that's the right answer, guys. The mass energy, many people kilonovas and black holes collisions, whatever this happening, the kilonova is basically the merger of the two neutron stars, exactly. So this kilonova, so it radiates the mass energy, this system of a neutron stars, the mass energy, this system of the neutron star, which neutron star has. Let me erase this guys first, okay? Okay, so the mass energy this two neutron star have, they radiate it in form of gravitational waves. So the mass of these neutron stars, okay, is get converted into energy. That energy is transferred in form of gravitational waves, and the same mass is what exactly stretching this L-shaped arms, is exactly stretching and swirls that arms. So mass of the neutron stars there, like many light years away, is coming here in form of gravitational waves, and that mass energy or that mass is basically stretching and squeezing and performing some positive work here on Earth. Isn't it interesting? It is, right? So neutron stars there is getting the part of their mass right here on Earth to perform some positive work. So if you ask me, like, what is stretching, like what's the fuel source of stretching of those L-shaped arms, I can confidently say it is the neutron star. It's the neutron star fuel that we are using. Isn't it very interesting? Yeah. So yeah, exactly. It is actually very interesting, guys. So one more question I actually wanted to ask you guys is that, okay, for example, I have this phone in my hand. I just switch off the light. Okay. So guys, just a second. Okay. So I have this phone in my hand. Now, when I release it, why does it move in space? Why does it move in space, guys? Many people say gravity, but I don't want that answer, guys. Okay, please don't say gravity. We're in a hyper relativity lecture. Okay, so of course it is gravity. I mean, but we are gonna explore like gravity, like I want to take some relativism what I taught before in this lecture, something related to that. When I just release this phone, why does it fall in? Why does it move in space? Remember what I said? The faster you move in space, the slower you move in time, and the faster you move in time, the slower you move in space. So why does it fall? Okay, so let me explain you guys, okay, that thing. So here we are the general special relativity. Let me grab a marker pen, and many people actually answering the correct, but I want to explain in exact correct form. You guys are mostly correct, like 98% maybe. Okay, so I can draw here, I think. All right, so this is my phone. All right, this is my phone. Now it is on Earth, it is under the Earth space-time curvature. Perfect. And this is the Earth, and this is the time of my phone, time dimension of my phone. This is the time dimension of my phone. Perfect. This is the time dimension of my phone. But since it is under the space-time curvature, the time has bent. This is just the exaggeration. It's in reality, time just bends maybe a small bit, like it's unnoticed. Okay, so the time bends a bit, and when the time bends, what happens? You slow down in time. And guys, what happens when you slow down in time? Look at the screen. What happens when you slow down in time? The same thing. I hope so you are looking at the illustration which I'm giving right here on the screen, my screen, not the slide, but what I'm showing here on my screen. What happens when you slow down in time? You speed up in space. So why do these things exactly you accelerate in space? So this phone is moving because Earth space-time curvature has slowed down time for it. And since time has slowed down, the tug of war, remember, the faster you go in space, the slower you move in time. And the faster you move in time, the slower you move in space. Relativity, guys, is all about this tug of war. It is all about this tug of war, okay? So that's the part of relativity. So do you wonder, guys, like right now, every single second we are here on Earth, so we are in a constant time dilation of the Earth. So what is its equivalent? For example, let's say, for example, if light travels at speed of light in space, it has no component in time, so it feels no time at all. But right now I'm in time dilation of the Earth, so I have some time bent, so I have slowed down in time a bit. So what is its space, what is its speed equivalent in space? And what is that speed? You wonder, since Earth has slowed down time for me, what is the speed equivalent of it in space? In space, no, it's not c. It is not c, because Earth, we haven't yet, I mean, Earth space-time curvature hasn't slowed down time to zero. That only happens on a black hole, guys, not on Earth. Okay, so here on Earth, okay, a tiny, like our time has slowed down a bit, but what is that speed equivalent in space? Since I explained this tug of war, so since we have slowed down in time, we have to speed up in space. But what is that speed? Since we are in constant time dilation, what is that speed? Look at the screen, look at the presentation. This is this exact speed. Okay, this is the exact speed we are traveling. Escape velocity. Perfect, perfect, exactly. It is the escape velocity. So it is the exact speed we are here on Earth, because Earth, as we know, the Earth space-time curvature has slowed down time for us, and since we have slowed down time, we have to speed up in space. Now the forces are here on Earth have been keeping us like with sticking, like we are stuck with, not stuck, but like we are here on Earth. Okay, but what is its equivalent of, like, in space. Okay, so this is the thing, 11.2 kilometers per second. So I can confidently say that I am moving at 11.2 kilometers per second in space, even if I'm not personally. But since I have slowed in relativity, this is the definition of speed. Okay, this is the definition of speed. Once you slow down in time, you have to move in space, even if you are not doing it personally. So that this bending of time is basically the space equivalent, the space equivalent speed, the speed equivalent of this bending of time is this exact number, 11.2 kilometers per second. But this is the case of the earth only. Okay, this is the case of earth only, exactly, with reference of space, with reference of a very inertial frame or reference of a rest frame. We all are moving 11.2 kilometers per second because time has slowed down for us. And since time has slowed down for us, we are all are on earth moving at this speed, 11.2 kilometers per second. Okay, so yeah, and this speed is all due to the theory of relativity. It's all due to relativity, all because of relativity. Okay, so as I explained, even this thing, like this slide right here. Okay, so we are heading towards like very really interesting part, guys. Okay, so same thing is happening here. So this is earth going around the sun. And why does earth go around the sun? Because why does earth move around the sun? Because time has slowed down, because time dimension, the time has curved. And when time has bent for the earth, the time has slowed down for the earth. And when time has slowed down for the when earth has slowed down in time, it has to move in space. Okay, since the faster you go in space, the slower you move in time, and the faster you move in time, the slower you move in space. And the earth has slowed down in time, it has to move in space around the sun, getting the entire year, getting it in the entire year. Okay, so this is what happens. So yeah, so I hope you guys understood really well. And also I have mentioned it really clearly. So we are really heading to very interesting part, guys. So read it. I want you to read it, guys, carefully. Okay, standing on the surface of any gravitational source, you can't claim to be at rest. Since you have slowed down in time, the remaining speed out of c must manifest in space. The same thing, why this is the reason why we all are traveling at 11.2 kilometers per second here on earth, as I explained. The same reason, on any gravitational source, it slows down our time. And since it has slowed down our time, we must move in space. There must be some space equivalent speed out of the speed of light, since this tug of war is all about that speed of light. Okay, so there must be some speed of light equivalent. Now, very interesting question I want to ask you guys. There exists a very amazing object in this universe. On Earth, it is like, for us, it is like moving at 11.2 kilometers per second here on Earth. Staying on Earth is just same as traveling at 11.2 kilometers per second in space. But there is an object in the universe being on which it is exactly same to travel at the speed of light in space. Guess what that object is, guys? I would love the answers in the comments. I'll read them out. Again, as I said, ha 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 ha. Wow, 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 wow. Amazing. Black hole. That's so that object is this thing. A black hole. Exactly. You get it? Staying on Earth is just like traveling at 11.2 kilometers per second in space. Staying on the event horizon of a black hole, on this point right here, staying here is exactly like traveling at speed of light in space. So once you have, that's why time doesn't run for anything that exists on a black hole. If you are here on a black hole, time won't run for you. If you are on a black hole, time doesn't run for you because you are actually moving. It's equivalent of moving at speed of light in space. If you are here on a black hole, it's equivalent of moving at speed of light in space. So that's the thing. And the fun thing about black holes is, guys, that it is real, and we also have an image of it. We also have an image of a black hole. So this image was released in like 2019, and it's really amazing. It was captured by the event M7 black hole, exactly. So it was captured by an event horizon black hole, and sorry, event horizon telescope. I'm sorry. Yeah, so it was captured by an event horizon telescope, combining the power, 7 telescope around the world globally, and captured this image. So guys, imagine standing here somewhere here is exactly like traveling at speed of light in space. Isn't it amazing? Isn't it interesting? Standing somewhere here is exactly like traveling at speed of light in space. This image was already predicted in Interstellar. Yeah, Interstellar black holes were like, it was like really great description of what black hole does actually look like in reality. So in this actual image, there is some angular resolution which these guys actually took it like from other side or something. That's the thing. But if the angular resolution was different, we would have had the same interstellar black hole, like what it actually looks like. So isn't it interesting, guys? But staying to the hyper relativity, isn't it interesting that staying here on the black hole is just same as traveling at speed of light in space? Perfect. So, guys, on the surface of a black hole, it's just like traveling at speed of light in space. But inside a black hole, the gravity gets so much strong. The gravity becomes so much strong. So, what must be happening inside a black hole? So, on the surface of a black hole, it's exactly like traveling at speed of light in space. But inside a black hole, the gravity gets more stronger. So does that mean that we are traveling faster than light? So there comes the questions like, this is the black hole or black hole. So there comes the question like, it comes the questions like post relativity, faster than speed of light travel, and the pseudo universe or something, the universe inside a black hole and all those stuffs. Okay, so there comes the questions like this. So what really happens inside a black hole? Let's discuss that. So on the surface of a black hole, it is exactly like traveling at speed of light in space. Okay, so at space we are traveling at speed of light on the surface of a black hole, but in the dimension of time we are traveling at zero speed. Remember that tug of war? The faster you move in space, the slower you move in time, and the faster you move in time, the slower you go in space. And that tug of war is all about the speed of light, and we travel at zero speed in time. Okay, that's on the surface of a black hole. But when you get inside a black hole, in this now I'm also gonna explain you how it feels inside a black hole, how it feels inside a black hole. Okay, so on the surface of a black hole, as I said, it's exactly like moving at speed of light in c and resting in time. But inside a black hole, the space becomes time, guys, and time becomes space. So what happens, this exact thing, right? Yes, inside a black hole, the metric switches. Okay, the space become time like and time becomes space like again. So same thing, time here, space here. right? And so since the switch coordinates, this thing remains the same. Okay, so now we again traveling at speed of light in time, and we are traveling at zero speed in space. What is this, guys? What is this? What? How does it feel like? What does it feel like? It feels exactly like being here in the normal universe. Many people are asking, like, why does that switch happens and all those? Because we have seen that switch. It's not something which many people theorize it, but it is also mathematically proven that inside a black hole, if you extend the relativity, the coordinate has to switch. If you, because guys, speed of light, if you actually see, we talked about it, that speed of light is actually the infinite speed of the universe. It is a speed which you can't overtake at all. You can't overtake at all. And if you try to overtake it, there always happen like a switch in coordinates. You get it? This is math. This is the mathematical result instead of some kind of a theory or something. It's a mathematical result. All right. So the same thing. Okay. So inside a black hole, on the black hole, we are traveling at speed of light in space, and we are resting in time. But after you cross the space and time switches it role, and it becomes same like traveling at c in time and resting in space. The same like what we are doing here in space. What we're doing in space. The same thing. The same thing are we doing in space. Resting here in space and traveling at speed of light in time. And so it is same like our universe. So sometimes it's also referred to as the pseudo universe, guys. Like what exists inside a black hole is like a pseudo universe or something, faster than sea travel and all. Yeah. So that's the thing. And there is nothing called the faster than sea travel, because the sea travel, the sea itself is infinity. Infinity plus one is still infinity. Infinity, you can't compare any speed. You can't compare any speed with the infinity. And you have to realize that the speed of light is the infinite speed of the universe, guys. Okay? The speed of light is the actual infinite speed of the universe. We have to realize that. So if you have watched the movie Interstellar, the reason why Cooper was actually alive himself was because his space-time was like stable, because it's exactly like he was inside a black hole, and it is exactly like being in the space, being in normal universe, because after you cross the event horizon, it is exactly like staying in the normal universe, as I just explained, due to the switched coordinates. But there comes something after this point when you are inside a black hole where everything sucks, guys. Okay? And everything goes into the destruction, people say. And that's the point of singularity. So in the very beginning of the lecture, I have mentioned like a relativity. What's the essence of relativity? I'm going to mention it again. All right. And that's the picture of singularity. Okay. The faster you move in space, the slower you move in time. And the faster you move in time, the slower you move in space. And this tug of war of C in space and time, okay, was defining the space-time itself. But wherever there is no kind of this tug of war in the hyperspace, there is no space-time, there's no universe. And this exact tug of war ends here on the singularity. The faster you move in space, the slower you move in time. The faster you move in time, the slower you move in space. This exact tug of war is not defined. It ends at the singularity. All right, it ends at the singularity, and this ending of tug of war. And so wherever there's the end of this tug of war, there's the end of the universe. We can't define universe there. We can't define space-time there. Okay. So it is all about it. Okay. So uh, the universe, guys, is all about this tug of war in hyperspace. Space time is all about this tug of war. So, guys, space time is all about this tug of war in hyperspace. And so, also, the name of my book, the Hyper Relativity. So, the universe is all about the relativity in hyperspace. Okay, it's really greatly and carefully discussed in this book. Like in 1 hour 2 hour lecture, the book, reading a book always make you learn more in detail, and see the links and actually understand the concepts and all. The book is also available on Amazon. You can always check it. So the universe, as I said, just relativity in hyperspace. So that's the concept of hyper relativity. Okay, and so that's it for today's lecture, guys. And yeah, so it was a great time interacting with you, and thank you a lot, guys. Thank you a lot. I'll be taking a lot of questions from you guys. Okay, and yeah, I'm dead.
Thank you so much, sir. What an amazing session. I mean, I got to know how accurate Interstellar was, but really good. I got to learn a lot.
Yeah,
Uh,
thank you.
yeah, I would suggest now that people got a lot of questions. Please do raise your hand and open your mic and camera to ask questions from sir. We'll take questions one by one. All right. Uh, okay, there, yeah, you can go ahead. Let me.
There, you can just turn on your camera.
You'll not be able to turn on the camera and like. Let's try.
Hello everyone. Hi sir.
Hello,
Sir, I just have a couple of questions. First of all, if we are traveling at the speed of light in time or close to that, as time does fast enough for us, because we are traveling at 11.2 kilometers per second due to Earth, couldn't the real age of universe be much larger than we perceive it to be? Because time moves a lot faster for us than it must in reality. We think that the universe's age is 13.8 billion years old. But what if it's much larger and we just perceive it to be 13.8 because time moves faster for us?
Perfect. That's really right. That's really an amazing question. So you're asking, like, if time has slowed down for us. So when we record the universe, record the age of the universe, is it that the universe can be older than what we are recording it to be? Well, when we actually calculate the age of the universe, it is not that we are recording it. Okay. So first, really what we do, is that we observe the expansion of the universe in general. Okay. And then we see at what rate it is expanding, and that rate gives us some constant. All right. And based on the size of the observable universe, okay, and that constant we get, we estimate the age of the universe. That if the observable universe, if the farthest galaxy that we can see is this wide, this far from us, then based on this constant, how much time it would have required to cover that, to go that far in space, and that time is what exactly we get it as the age of the universe. So it's not something we record it. If we actually record it, then your hypothesis like quite holds true, but it's not that we record it. It's the age of the we calculate the age of the universe based on our observation. So based on, as you said, the Earth space-time curvature, it might slow down time for us. So based on so to be honest, the Earth space-time curvature has slowed down time, but that effect is so tiny to even consider, like even a bit, as compared to the age of the universe. You get it? So it's very tiny effect. It's a very tiny effect. It does, of course, has an effect, to be honest, if you actually think about it, but the effect is very, very tiny to even consider. But yeah, that really is a good question. So it does affect, but tiny, it's very tiny to even consider. If you consider time dilation due to the Earth, try calculating for yourself. So it's very, very tiny. It's very, very tiny, and tiny enough to let's not consider it. Okay. It doesn't. So the age of the universe is 13.8 billion years. And if you consider the time dilation effect of the Earth, even for like thousands and lakhs of years of our recording it, so I mean measuring it, so that is not even a thing to consider, because the time dilation of the Earth itself is like so tiny, as compared to the star. It is you can actually, there is some measurable effect, but not for the Earth. So yeah, but it was an amazing question, by the way. Really liked the question. Yeah.
Thank you so much, sir. Sir, I had another question. As light travels through space with speed c and does not travel through time, time is basically reduced to zero for light, right? So why isn't space reduced to zero for us when we travel through time at speed c?
Well, to be honest, that's what we call the Lorentz contraction, if you actually know about it. Like space contracts if you travel at speed of light. You said it right. The thing is that light doesn't travel in the dimension of time. Time exists for light, okay? Hyperspace is always there. Time exists for light, but light just doesn't travel. For example, this is the dimension, okay? It does exist for me, but I'm not traveling in that dimension. It doesn't mean that it is zero for me. It does exist for me. At the end of the day, the zero to infinite number of dimensions do have its original existence, but it is just about our choice. If we want to travel in dimension of time, what if you ask me if I want to rest in time, what will I do? I will travel in space at the speed of light. This is how I rest in time. And if I want to rest in time, rest in space, what will I do? I will travel in time at the speed of light. For light, to be honest, time does exist, but light doesn't choose to travel in time. That's it. That's the only thing. It stays at rest in time, but any dimension ranging from 0 to infinity in hyperspace all exists for light. Or it exists for you, it exists for me, it exists for light.
Thank you so much.
Same thing. I hope this answers your question, right?
Yeah. Just one last question. I'm so sorry for extending.
Sure. Please.
We have seen that gravitational waves and electromagnetic waves, these largely travel at the speed of light.
Yeah.
So, my question is, because they do not perceive time, why do these waves get weaker the farther they move away?
Well, the farther they move away, due to the expansion of the universe, all right, the universe gets stretched, okay? And as I said, matter, space-time, and relativity, these all three things coexist because matter needs the existence of space-time, okay? So the existence of matter is linked with the space-time. And whenever there is this space-time stretching, okay, space-time, it's not actually stretching. When you say the universe is expanding, it's not like a balloon expanding, but it is that this new space-time points are coming into the existence. So that energy kind of gets distributed in newly created space-time, creating that overall effect of reduction in energy. So it's mostly due to the expansion of the universe, I will say.
Okay, thank you.
Maybe for EM waves, maybe it's for the gravitational waves, unless and until it has created some positive. That's why, you have asked a really nice question. That's why we say, the first law of thermodynamics, that energy can neither be created nor destroyed. That only holds locally true. Globally, the energy can be stilled. You can still the energy globally. That's why the first law of thermodynamics, you can actually study about it. The first law of thermodynamics only holds true locally, not globally for the entire universe, because there is some energy loss due to the this expanding space-time. You get it?
Okay.
Yeah.
Thank you so much, sir.
Yeah, love to answer it. Yeah.
Thank you so
More
much.
questions, guys? Yeah.
Thank you, Dar. Rudra, you can go ahead now.
Hello.
Hello.
Can you hear me, sir?
Good evening. Good
First of
evening.
all, good evening, sir. So first of all, I would like to say thank you. This is my first I've attended this kind of meet, and you explained it very well, with
Thank
great
you.
examples, like that tug of war, and actually I'm an 11th grader, and I'm very interested in this space and all stuff.
Space-time.
So
Yeah.
So my question is, what happens at singularity? Like in the movie Interstellar,
Okay.
Cooper, like when he goes into the black hole. So like, can we change dimensions? Like, do we go to another dimension at singularity?
Well, in the movie, if you talk about, they were mentioned. They always mentioned someone called they. You wondered who were they? They were the bulk beings. Those are the higher dimensional beings. And those actually, they didn't mention them explicitly, but they actually mentioned them like they, in the form of like they. Who are they? Like, if you actually check it. So these bulk beings actually created a four-dimensional tesseract before Cooper falls into the singularity. Every black hole has a singularity in it, but before the Cooper falls into the singularity, the this bulk being actually traps the Cooper inside that box, four-dimensional box, and where he was operating that everything. So in the actual black hole, we don't have such things. Actually, we don't study one, but in the movie, it's greatly described that the bulk beings actually created that tesseract and everything. But I don't think it's real in real life. It's possible. No, that the Interstellar movie is actually incredible. But to be honest, yeah.
Yeah, that was my question. Thank you, sir.
Thank you. Thank you. Nice question.
Astrobot, now you can go ahead and ask your question.
Yes, good evening, sir.
Good evening.
Yeah, I had one question. So, in this hyper relativity, like how many dimensions could like in one theory could there be? Because like, see, as you said, there could be infinite amount of dimensions. How many dimensions would be needed to let's say unify all the forces,
Well,
like
I got you. So there are various theories in actually physics. For example, if you heard about Kaluza-Klein theory, which
yes,
actually talks about the extra dimensions and all those. But in ideal conditions, it takes, I think, I'm not into string theory. I'm a gravitational astrophysicist, but I have read about the string theory. So it takes to unify around 11 dimensions. It takes to unify all the fundamental forces. If you actually want a single strong force, that's the goal of the grand unified theory.
yeah,
So it takes around 11 dimensions of the hyperspace to unify, to explain at least like how to unify all of these fundamental forces. And right now we are working with the quantum gravity, and we try to unify the all the forces with all three forces with the quantum, quantum mechanics. So that's under the process for sure. Gravity and quantum mechanics.
yeah.
Yeah,
And
11
yeah,
dimensions. Yeah.
yeah. My second doubt was like, like, could there be dimensions that can be smaller than a proton, which which could be folded using what do you say, z square, z base 2 symmetry, which is, you could say, an orbifold. So using that, they leave two special boundary points, okay, which in that theory could be called brain
M theory, you are saying.
M theory. Yeah, you could. Yeah. It's M theory. You could say. Yeah.
So yeah, that's a membrane theory. So if you actually, yeah, please continue your question. Yeah.
Yeah. So say that like we could unify all the um, forces of the universe into only say six dimensions uh, using an orbifold and an and a lattice, a six-dimensional lattice.
Yeah, exactly. We can actually do that. And I mean, that's the kind of solution. But the main thing we are actually, I mean, there are a lot of solutions in, and we have much, if you consider really the M theory, we have like all the best, like if you combine like a lot of solutions, we have the best solution for M theory plus string theory. But the problem we are really facing is like unifying gravity and you getting the quantum mechanics. That's the only problem we're facing. That's like a point where if it's solved, we know how to unify all the forces. Okay.
Yeah.
So that's the thing. So that's the only thing we are waiting for. All right. And yeah, so M theory, in fact, summarizes everything in the best. Like, you get it?
Okay. Well, I have worked on a theory which says all of this. It solves all of the problems.
So
of
you
general-
personally worked on it.
Yes, with my friend.
Okay,
I-
amazing.
Yeah.
By the way, are you in 11th standard?
Oh no, I'm going to go to 8th.
Oh, wow. At this age, I mean, you are really working on really great things. I really appreciate it. And keep working on. There is nothing called age limit or something, and
Yeah.
just keep working. Yeah.
Yeah.
Keep
So
working.
I was just wondering if you would also want to work on this, because we have some problems like the fermionic statistic problem is also there in our theory. So yeah.
I got you. So you're facing some quantum mechanic problem in quantum mechanics or statistical mechanics.
Yeah, you could say it like that. Yes.
So quantum mechanics, I mean, of course, if you face some problem in quantum mechanics is like that, because the best way you can understand the quantum mechanics is not understanding it really,
Yes.
to be honest, actually.
Yeah.
So you get those kind of problems. But if you actually really work hard, if you ask, you can even ask me for a help in case you can show me off equations. I will really think about it if I get time. Okay. So
Yeah.
I might love to help about it. Yeah, for sure.
Yeah, sure. So I think I've sent the paper in the chat.
You can send it me on like maybe I will like you can communicate me to the one who has
So
like,
Ash will send it
Okay,
to
sir, I'll
Sure.
share your contact with him.
sure. You can send it to them and they will send it to me. All right. Even your contact or something, email or something. Or
Yeah.
I will send in my email to you.
In the paper, like this is my email. So if you want, you can contact me if you want. This is my email.
All right. It's pretty simple. Okay. Astroking 30. Okay. I will
I'm
show
sending you
you.
in chat, sir. Yeah, I'm sending you in your WhatsApp.
Sure.
Yeah.
All right. You have any other questions?
No, I just it was just that, and yeah.
Yeah. Amazing. Nice energy, boy. And just keep working hard, on your dreams. There's nothing called age bound. You can do anything at any age. Okay. Just keep working. All right.
Thank you. Yeah. Thank you. Bye.
Bye.
Great
More
question.
questions?
We'll take Naveen's questions now. Naveen, you can go ahead and ask your question.
Yes, sir.
Hello, Naveen.
Sir, my question is, whenever a person gets near to a black hole, time starts to slow,
Okay.
and when he reaches the event horizon, it stops. So, does that person ever reaches the black hole? Does when?
So in his own frame of reference, he always goes inside a black hole. He touches the black hole. But it's all about this game is all about the reference frame. Okay. So for someone who is really, really far away, for him, he never touches a black hole. You get it? But in his frame of reference, he does all of the stuff. Okay. So for example, if a star forms a black hole, then the original material with that star has form a black hole from, it all is still there on a black hole, because from a far frame of reference, everything is stuck there because time has slowed down for it infinitely. So time doesn't work for it because time doesn't run for anything over the black hole or near to a black hole. So it's all about reference frame. So if you are near to a black hole, you can see person falling inside a black hole, but if you're far from it, no, it's always stuck there.
So that person never actually reaches the event horizon, right?
Yeah.
Okay. So, sir, I had one more question. So, can the stretching of celestial bodies be explained by relativity? Like when an asteroid gets near the Earth, it stretches. So, can this be explained by relativity?
When an asteroid gets near to the Earth, it stretches. So we are saying tidal gravity.
Yes, sir.
So in reality, like tidal gravity is all about I don't think because tidal gravity comes the most in Newtonian mechanics, to be honest. Don't think that there is no much application of relativity here, because tidal gravity is comes under the Newtonian mechanics. We don't need to deal with relativity in case of the tidal yeah, I mean, for tidal gravity itself. Relativity is all about near to the speed of light and all those things. It's about gravity. So I don't know. No, it doesn't actually. We can actually solve it through tidal, Newton mechanics itself, I think. Yeah.
Okay, sir.
So any other questions, Naveen?
No, sir.
No? All right.
All right, Naveen. Dhanvin, you can go ahead and ask your questions.
So I have a couple of questions. I'll ask you few of them.
Sure, Dhanveen. You were active like throughout the what to say lecture. I really appreciate it. Go ahead, Dhanveen. Yeah.
Thank you. So yes, there's this thing called compactification. So when you get extra dimensions, they get compactified into certain tiny geometric shapes. So I mean, yes, they do get compactified. They do get compressed into these shapes, but then where do these shapes actually go? Like, do they keep hanging around the other dimensions, or do they just vanish?
I mean, you said in extra dimensions, the shapes keep forming. All they do actually exist because in extra dimensions, if you actually look at it, there exists nothing called time. So you can't use the word forming. Or either
That's
they
true,
actually do exist or they don't. You get it?
They
Because
don't. Yeah.
when you don't consider the universe in hyperspace, when you consider time, I always say that the creation of time is the creation of the universe in my book Hyper Relativity. So if you just talk about random dimension hyperspace, there's nothing called forming, I mean, or creating. The structures are like they either created or I mean, imagine like for example, you are in school right now, you are in college right now, so everything exists all of a sudden. There is no such like time gap or something. You get it? So if there exists structure and there is nothing called forming and like just exists. I hope so. That was your main question, right? Isn't it?
It kind of was, but then I was asking, where do they go? Like, do they just keep hanging around the other dimensions, or do they just vanish?
So where do they go? The term "go" is all about time. You're getting either they or everything exists. I mean, the human mind tries to think that way. Where does it go? What
True.
happens? What will happen next? But that's
know,
the
but then-
question which takes into account that time exists, but time doesn't exist there. So any kind of shape, even if to consider that shape, okay, to consider that shape, I'm writing a new book right now on the existence, like the way we count. For example, you are considering it as a shape, but if I personally choose to not consider it as a shape, and it's just not different from the hyperspace, it's just same as the hyperspace, then that perspective, even if you actually look from that perspective, it's not wrong. You're getting it? So even if it's like some bizarre shape, it's still not different from the hyperspace because hyperspace is all about that weird stuff. If you actually see quantum foam, I understood your question basically. So if you see quantum foam, there's always that wiggly shapes and all like happening there, without existence of time or something. It's always happening there, like quantum foam. So it's either there, and why to even care for its existence? Like, you getting?
True. I mean, they're not exactly very important.
At least to physics, because physics is all about understanding the universe.
Yes.
Yeah, you get it.
So I have another. Say there's a black hole and there's an asteroid getting drawn into the black hole for some reason. And humans have achieved space flight beyond the moon, and let's say a guy is currently on that asteroid.
All
What
right.
would happen to him? Like, would he get stretched out? Like, what happens if he fell directly into the asteroid, or would he somehow merge into the asteroid and then get pulled in or something?
You must have heard about the spaghettification.
Yes.
So once you go near to a black hole, the tidal gravity is so strong that you just get stretched like a spaghetti, like a noodle.
Yes.
Okay. So you get stretched like a spaghetti, and that's what spaghettification is. Now, in case of smaller black holes, the tidal gravity works in a way that even for a human-sized object, it has so much strong gravity that it can actually tear apart the entire human body. Okay. But if you actually talk about the larger black holes, and if you talk about the tidal gravity of them, they're not that harsher as compared to the smaller black holes. The tidal gravity is not that harsh. So maybe an asteroid or a human may survive there. That's why in Interstellar movie, if you have watched it, the Gargantua black hole was much safer because it was a huge black hole and it was safer for a human to voyage into it. and that's why the Cooper, the main astronaut, was still was safe going into it. Yeah.
A last doubt. I
Sure.
read the series by Stephen Hawking for children, George. Have you heard of it? It's about a
Uh,
kid.
no, I haven't heard of it. It's a Stephen Hawking series, you're saying?
Yes, Stephen Hawking
Okay.
and his daughter. Yeah, they wrote it. It's like about a kid named George, his friend Annie, and they have a supercomputer
All
called
right.
Cosmos. And now this computer is exactly like a normal laptop, so it can sketch portals and transport them to different places in the universe. So, in one such adventure, one of George's friends named Eric, he falls into a black hole, and then Cosmos manages to do something and rescue him back out from the black hole.
Mhm.
So, what happens there? It's something like Cosmos manages to speed up the time, so the black hole gets destroyed or something. It starts compressing and then it randomly explodes. So, all the particles which were Eric come out in that explosion, and Cosmos manages to reconstruct them again. So, could this happen in real life?
So that's what you are really saying. There's a term for like entropy. Do you know entropy? Like
Yes. Yeah.
yeah. So it will create a really high entropy. If you it will create a very low entropy, not high, low entropy condition. If we have the particles and the, even if you stitch them down, but the chances of replicating the original are still very, very low. And something I don't think the universe really allow to actually perfectly mimic it. And if you do even have mimic it, but I don't think it's you can actually mimic it full 100% because that's really a low entropic thing. And the entropy, unless and until you create an increasing entropy on the other side, I don't think you can create the perfect structure out there. So I will say, yeah, it's a low entropic condition. Universe doesn't allow low entropy, but unless and until you create some high increasing entropy, which actually balances the created low entropy with that, uh, then you can create it maybe. For
I
sure.
thought this
It's
was
based
my
on
last.
what technology you have.
Yeah. So I thought this was my last, but then I have another. That
Sure,
is,
sure.
what would a 4D object actually look to human eyes if I just got one and placed one right in front of me?
Let's take a cube, hypercube. Take the tesseract, the exact thing like which I showed you in the like the
Yeah.
beginning of the lecture. So the human mind actually think it just can't think more than 3 dimensions,
It can
right?
process. Yes.
Exactly. You can't actually think about it. All right. So if I just get a 4 dimensional tesseract in front of you, the side, you know what is the side of a tesseract? It's a cube. The side of a cube is a square, all right? But the side of a tesseract is a
Is
cube.
a cube.
Exactly. So just like any point you see of a cube, either you're looking at its side or either you're looking at its edge. So if you look at the edge of a tesseract, you will see a 2 dimensional plane. And if you see the side of a tesseract, you will see a cube. You get it?
So it
And
looks weirdly distorted.
exactly. And if you see the very edge of a tesseract, okay, that very edge will look like a line. That's how bizarre it is. Okay, that's how bizarre a tesseract is. 4D object,
Very bizarre.
something that a human mind can't understand. Yeah. So
Thanks a
you
lot.
are in which you're studying in which grade?
9 right now.
Oh wow, really amazing, guys! Like a lot of young people are actually getting into stuff. I really appreciate it, guys. Really amazing. Keep
Thank
your
you very
speaks
much.
on it.
Thank you, sir.
It's amazing, guys. Nice questions, by the way. More questions, guys?
All right, Yuvraj, you can go ahead and ask your questions.
Sure.
Sir, thank you for able. It was really beautiful and really experience. I really got so much things, and thank you, Propagation Institute, for able to conduct this session.
Thank you,
So
Yuvraj. Thank you.
my question would be like, if it's very theoretical, but if we can possibly get into hyperspace through any
Okay.
machine, and we know that it's frozen, like time doesn't exist, past, present, future, all exist at one time, theoretically. So if it's like a record, frozen record, if we could change a part of a past, like I think that's how time travel can be possible. If it's possible, will it change the hyperspace itself, the time of past, present? If we change a part in past, will it change the record? I mean, you are able to get it?
I got you. I got you. So, first thing is that I'm against the time travel in past. You know why? In one of my podcasts, I have explained it really, really well. Okay. So let's say, for example, in past, there are 10 people. Okay. There are 10 people in the past. All right. Now, if you time travel in past where there were 10 people, you add an extra person. How many people it becomes? 10 plus 1, 11
11.
people.
Yeah.
So what does that mean? It means that you never traveled in time, because the point where you actually wanted to travel in time, it only had 10 people, but you landed in a place where there are 11 people right now. So it can never be considered as the actual time travel. Okay. So your question was like, does this process, even if it happens theoretically, if time travel happens theoretically, let's say by any means, even if time travel is not possible, if it happens theoretically, does it change the hyperspace structure? Well, to be honest, I mean, throughout my book Hyper Relativity, I have actually proven, if actually read the entire book, I have actually proven this, that the universe, the existing universe is exactly like it not existing. At the end of the day, even if time exists, it exactly is like not existing at all. At the end of the day, the universe itself is a hyperspace. At the end of the day, the universe itself just a special case of hyperspace. You get it? It belongs to hyperspace, and it is just a special case of it. It is just, so anything you do with the universe, at the end of the day, it is going to stay in the hyperspace. Even if you create the universe, it is the hyperspace. You create the universe, it is the hyperspace. You destroy the universe, it is still the hyperspace. So I have proven it really step by step in my book Hyper Relativity, and so you guys can actually read it if you're not on Amazon. I mean, so
Yeah.
at the end of the day, whatever do you do with the universe, it is the hyperspace, and hyperspace is like that structure that it's omnipresent, and it's like you can't create it, you can't destroy it, just like everything is just special case of it.
So my another question is like, when I was going through many books or like even through podcast or through this session itself, I got a genuine doubt that why everything is so balanced and feels like as if it needs to exist so that the other concept can live with it. Like how to tell, everything exists for a reason. So why that is so perfect? Why everything is there for a reason, and why space is not chaotic? That's my question.
If space was chaotic, there wouldn't have been question askers, and the
That's true.
who decides what is chaotic or not? Humans.
That's true. Hmm.
At the end of the day, there is nothing called chaotic, and there is nothing called non-chaotic. You get it? At the end of the day, there's nothing called chaotic, there's nothing called non-chaotic. The only one who makes like the only one who makes the difference in between chaotic and non-chaotic is the human. If we actually look from a physics point of view, okay, in general, if there were no humans at all, who would have said that this is chaotic or this is non-chaotic? At the end of the day, nothing is chaotic, nothing is non-chaotic. It's just the labels we have given to them. All right. So there's also saying that everything is for reason, and that can actually hold quite true. Why not? I mean, if you say that everything holds for a reason, I won't say that there's no reason for anything, because there are infinite chances in the universe. There are chances that everything is created for the reason. There are chances. So I respect the fact that everything is been created for a reason, but I also respect the fact that everything has been created for no reason. I respect these two facts, and also I respect another third fact, that there is an alternate reality, the third reality, which which transcends these two realities while explaining them yet. So that's my part of new book again, and yeah. So
So
we have to
final
respect
question.
a lot of facts.
What type of technology have to be developed to perceive other dimensions in your sense? Or is it just our consciousness, whatever philosophically, spiritually we tell about, is it related? Or what type of scientific technology have to be developed to able to perceive that kind of dimensions?
we actually do perceive dimensions from many years, and that has been in terms of mathematics. We have been dealing with the extra dimensions with mathematics since a very long time. Okay, so many, like from ancient India, if you actually see the multiple hands of the gods right there. Okay, like there is a like lot of knowledge about the extra dimensions in the ancient India itself.
I mean, not
So
mathematically, so physically, any kind of technology.
physically, technology, right, in terms of tech, the modern tech, we don't have any, but we can or not. Mm, to be honest, I mean, it's really hard to tell because the human mind can't even think about, if dimensions is A to Z alphabet, then we can't even think about A. You're getting my point? So how can we build a technology which actually thinks about the extra dimensions? And mathematics does. Through mathematics we can, but I think mathematics is the best tool. Even if we do it, even if we build some technology, we are going to do it with mathematics at the end of the day, I think. You get
Yes,
it?
sir. That's it. Yeah.
Yeah.
Thank you, sir.
You have any questions? It was like amazing. Like, yeah.
Yes, sir. That's it. No other questions. Thank you, sir.
Yeah, sure.
Thank you.
Sir, before we go ahead for the question or things, there is a lots of students. So what I really want, could you just suggest them a pathway how they can just start learning about the relativity? Because most of the people, whatever the question they are asking, it's being a little bit generous one. So if they would be able to learn about the relativity in way more better way, this would be better, I guess. So could you just suggest some books and the things so they could just go through it?
So first, read the very general level book for those who like in maybe 10th or 11th standard. I will suggest is the Relativity by Einstein. It's and you can get it on Amazon as well. So it's really simple. And of course, you can try my book Hyper Relativity as well. I have mentioned no mathematics in it, but for relativity, for you to understand relativity a bit, you need a little bit of mathematics initially. Okay, so my book Hyper Relativity assumes that you know that mathematics, then it deals with the not non-mathematically, but at the very best, it's not like we have integrals or differentiation out there, but okay, like minus plus or maybe some kind of multiplications, minor multiplication. So we can always have the Relativity by Albert Einstein. It is available on Amazon, so you can read that book. And also there are like a lot of books by Kip Thorne. If you know the professor Kip Thorne, you can read The Black Holes and Time Wars by Kip Thorne. And again, I will say, if you want to learn about the hyperspace, my book talks about the hyper relativity. But in case you want to learn about the hyperspace and string theory and all those stuffs, I will say the Hyperspace by Michio Kaku is also good. And if you want to study in detail about relativity, then Gravitation is also another great option. Okay. And again, we have books by Stephen Hawking as well for beginners, like for example, this Great History of Time and the brief history of time, and like a lot of books. And again, if you want to learn about like the geometry of relativity, then you should go with the books by Roger Penrose, like The Cycles of Time, like Roger Penrose, The Road to Reality by Roger Penrose. And yeah, a lot of books. And of course, do get Hyper Relativity as well. It explains relativity, and it's like broad explanation what I explained today. So yeah, this is one of the best relativity books I can suggest. So initially go for this Relativity by Albert Einstein. It's really explained in very like detail, and it's a small book, like maybe around 150 pages. That's it, not like a huge book or something.
Okay, sir. Now you
Right.
can just go ahead.
You guys have any questions?
Lakshmi, you can go ahead and ask your questions.
Okay, so thank you so much for the wonderful.
Thank you, Lakshmi. Thank you very much. Thank you, Lakshmi. It was a pleasure being here.
There is some network issue, I guess.
From my side.
No, from Lakshmi side, I guess.
Okay.
Basically, she was having a question. She has mentioned in the text as well. What happens to a soul? Wait a second, sir. I'm sending you to a soul.
Okay.
Our consciousness when detached from the 3D reality. So maybe, but she won't be able to hear it.
So is this the question?
Yes, yes, yes.
Please, can you repeat the question again? I just want to hear it once again. Your voice, please. Can you just?
What happens to a soul or consciousness when detached from 3D reality? Okay.
Okay, so what happens to the soul and consciousness when it detaches from the? So in a higher dimension, the creation, for example, let's say if I want to eat an apple, there are two types of creation. Okay, one is symmetry tending creation, one is non-symmetry tending creation. All right, so for example, I will tell you in short like what is the difference between, for example, I want to eat an apple in higher dimension. What will I do? I will just swap my fingers like a Thanos, and I will create, Thanos of Infinity Wars and the Avengers, and I will create an apple. That's a non-symmetry tending creation. But in lower dimensions, like in the one in the universe, like the 4 dimensions, not in lower, but I will say in the limited the number of dimensions, like in our universe. If I want to create an apple, how will I create it? I will create a Big Bang. Then I will create stars. Then I will create the planets, and then I will create the then I will create the planet like Earth. Then I will create trees, then a tree like mango, and then mango. Sorry, then I will create a tree like an apple, sorry, and then apple. Okay, and that's the way of creation in our the limited 4 dimensional reality. Okay, so once soul surpasses that external view of how higher dimension work, one starts to think that if I can, as a higher self, if higher dimensional self can create apple in like this with a snap, what's my purpose in this 4 dimensional universe where I can actually create the app, where it takes so much effort? Why I'm doing all this effort? Then comes the questions like God and all, where we actually say that no, I'm here in this universe just to work for God. You're getting, because this universe requires a symmetry tending working process to achieve anything. Okay, the higher self is infinitely intelligent. It can create anything even within this universe. But why do we take time? Why do we take work? Why do we have to work hard in this 4 dimensional universe? Or why even we doing so? So that's the part. That's the question we ask when we extend our soul into the, when we understand when we acknowledge our high dimensional self, our higher dimensional self. Yeah. So that's what the questions we ask, and we get a stage more closer to the reality. Okay, so that's what happens, and then we know God better even. This question.
Tanuja, I would request you to please turn on your camera and go ahead.
Okay, so thank you, sir, for this interactive session. It was really good. I would like to ask some of couple of doubts. My first doubt is that how would you explain the Einstein-Rosen space bridge that we encounter the after collapsing into the singularity of a black hole?
How will I explain the Einstein's Rosen's bridge after?
After an object or something collapses into the singularity or it reaches singularity.
After the singularity, the space-time ceases to exist. And Einstein-Rosen bridge requires space-time to exist, right? So after anything collapses into the singularity, we can't create Einstein's Rosen bridge, right? So you can't do that after that. So since everything collapses, space-time doesn't exist after the singularity of a black hole. That's the thing. So we can't form the Einstein-Rosen bridge, or AKA also known as wormhole. So we can't actually create it. Yeah.
So my second doubt is that as we say that some people say that the time travel is not possible, and some people say that it is possible. Then how would we explain that? For example, we can take Nikola Tesla when in one of his research he exposed himself to high electricity or high voltage, and in that time after that experiment he wrote in his research that he could see or coexist at the past, present, future in the at same time. So how could we explain that in the sense of a as a time travel theory?
So instead of explaining it in time travel theory, if we actually take a hyperspace view, like of actually treating present or the only real thing, well, the picture is that past is information, future is also information. The only thing real is the present. May it be like whatever. For example, the question you asked me just now was just like a minute ago or something. So that was not real thing. What I'm explaining right now is the real thing. So the present is the only real thing. You getting? So whatever information was there, even if we classify it into the past, into the future, that doesn't necessarily mean that it had some existence in the past or in the future. The present is the real thing. That is, this picture of treating present as the only real thing is called presentism. So Nikola Tesla might be even said that all time must be existing right now. That's the idea of presentism, that I can see the past, I can see the future based on his knowledge, but anything and whatever there is real is this present. Present is the only real thing. That's the idea of presentism. Perfectly. So might be, I don't know. Nikola Tesla, like a lot of years ago, I don't know what his picture really was. Again, but that's my
Okay.
estimate. Might what he might meant.
Yes. For my final doubt, sir, I just want to ask that why does the matter, or for let's take a star or any planet, why does it need to get so much squished up, like so much squished up that it becomes a black hole, like really small? For example, if we take Earth, so scientists say that if Earth wants to become a black hole, so it would have to be theoretically squished up in the size of a small pea bean. So why does the
I got
matter
you.
need to be squished up so much?
Okay. So in my this lecture, I explained you guys that the faster you move in space, the slower you move in time, and the faster you move in time, the slower you move in space. So to create a black hole condition, you need to travel, create a condition that it is exactly same, that we have to create a condition that it is exactly same to travel at speed of light in c, and it takes infinite amount of energy. But of course you can create a condition where your motion in time dimension is itself zero, and it takes a lot of force that matches the exact moment like what few stars can create through their gravity. Okay, and that exact force is what creates that condition where the time is equal to zero for anything that is in that space time frame or in that frame of reference. So that star or whatever, for few, some stars don't form a black hole, they form the neutron stars. Some stars don't form neutron stars, they form white dwarf. You get it? Our sun is never going to form a black hole, it's going to form a white dwarf. So for those some stars who actually form a black hole, there is right amount of force to create that exact condition where time is equal to zero. And when time is equal to zero, the entire tug of war is in space side. And now the thing is exactly like traveling. It's exactly same to consider that that thing is actually traveling in space. And that is why we can detect, okay, we form a black hole. So the main answer is that, main conclusion is that it requires the right amount of force to condition that t is equal to zero. Okay, you get it?
Okay,
And that
yes, sir.
force is achieved by that thing. That's the mathematical
Thank-
answer.
That's all. Thanks.
Yeah. Okay. Thank you, Danuja.
I think we are having the last question from
Sure,
Biswadeep.
sure.
Biswadeep, please turn on your camera. And whatever the doubt you are having, just Biswadeep. I think we are done, I guess.
Okay, we're done.
Oh yeah, sir, almost done.
Hello, sir. So my question is like, can multiple timelines of the same universe exist, which are like running at different paces, and hence some slower ones correspond to our past?
So you're saying that can multiple timelines exist in this universe? After that, I couldn't hear it clearly. I couldn't hear the question clearly. Please, can you repeat it again?
So like, can multiple timelines of the same universe exist, which are like running at different paces, and hence some slower ones are like corresponding to our past?
Within the universe, for ourselves, for anything at which we are at rest. Okay, so in Minkowski space-time diagram, if you have noticed, like nothing can go more than 45 degree. Okay, and the time travel backwards in past is like moving that 45 more than 45 degree to like around like more than by if let's say you are tilted by this like 45 degree, then what is 180 minus 45 degree? It's 135 degree. Perfect. So you have to tilt your world line 135 degree more than this. So for a normal thing, for a normal object, attaining 45 degree is not possible in this universe. So the most possible world line anything in this universe can possibly have is in between that light cone, which that 45 degree thing is the highest thing it can have in that 45 degree range, but not more than that. So either the world line can be only in this particular cone, but it can't go more than that. That's it. It has to stay in that. So only the world lines exist which remains in that 45 degree created cone. If you have watched the lecture, okay, so not more than that. Not in That's why past is not possible, and not even more than 45 degrees possible, because if you cross that 45 degree angle, you go into the pseudo universe, some other universe you get. That's what the part inside a black hole comes, right?
And if
So
like
only
there is an and if like
so
there is a
only
fifth
what I mean,
dimension,
yeah, please go ahead. There is only
a fifth dimension of time, which like allows the sideways, like traveling sideways in time.
Well, yeah, it's a really nice question. So many like once was having a lecture, and one of the student asked me like, there be the universe where there exists two dimensions of time, like the fourth dimension plus fifth dimension? Of course. So we might have to wear two watches then, like first see time on this first watch, then maybe on second watch. So of course, this is a high dimensional solution. And the wormhole, what do you say, can we have a fifth dimensional time to travel in? We of course can have the fifth one, but we haven't seen any like yet in our universe. Topologically, geometrically, we can have, but we don't know how to create it, or with the best the nearest possible solution for such kind of travel, like in time from higher dimension, is a wormhole, not like another timeline. But maybe in hyperspace we can create the universe where we have three dimensions of space and two dimension of time, or maybe even again three dimension of time, who knows. So topologically the possible solution. Yeah,
Okay.
nice questions, Bijoy.
I think we are done, sir. Like,
We are done.
yeah,
Doesn't pressure here.
yeah.
I mean, great questions from everybody and very great answers.
Yeah, and really like young kids, and like they are really enthusiastic about these topics, and they must be, because it really takes a nation ahead.
Yeah, I mean, great crowd and the great teacher.
Exactly.
This
Thank you
is
very much.
By the way, thank you so much, sir. You really
Yeah.
took all the
Really
questions very
coming
calmly, and it was really amazing session.
Thank
Everyone,
you.
please turn on your camera. Like, sir, what we usually do, like after the session, we just took a picture of the session.
Sure.
Capture this moment. So everyone, please turn on your camera. Astro God is ready. Everyone just turn on your camera.
Yes,
And the people
join.
who just want to connect with each other and all, okay, I've been sending you the link in the chat box. You can join that group. Everyone is there. So yeah. There is a lots of people who's not turning on your camera. Please do it so we could just capture this moment.
I have got one last question, please.
Yeah.
Sure. This is
Uh,
sure, sir.
Actually, it is very interesting to study astrophysics because it is a very interesting subject. But can you tell me what are the scope of services getting a job in India? Where can I get the job in India?
In India, of course, you can be a planetary physicist if you're talking about, because right now in India, okay, the search for the exoplanets, for example, for maybe aliens, and or for maybe like for research purposes, there are lots of post right now initially has started creating in India in organizations like ISRO, in organizations like TIFR, which is the Tata Institute of Fundamental Research. So you can be a planetary astrophysicist there, and again,
Mr.
in
Hiten,
astrophysics,
Mr. Hiten, just to stop you. I mean, my son is doing postdoc at UCLA on exoplanets.
Okay.
But he has told me that nowhere in India they are working on exoplanets except NICER, Bhubaneswar.
Oh wow, that's really amazing. So right now in universities in India, I think it's not possible because me myself are done from University of Lancashire in London. So in India, but there's have been like few posts based for planetary physicist, like job posts, not for study but as a job post. So my friend actually is a planetary physicist and he's applying for it at TIFR for this thing as a planetary physicist. So if one actually learns it as like a foreign degree or something, he may apply that at TFR, or maybe he can become a professor here or something.
Yeah, he's trying to do that, but nowhere is he's getting a suitable post for anything on exoplanet.
Right?
Not in TFR, not in IUCA, not in IIT, nowhere. Only in NICER there are two faculties.
In which?
Sir, ISO is also a good place.
Yeah,
I know that IC is a good place, but they are not working on exoplanets.
What PRL is doing, sir, I think you should ask him to check out the PRL. PRL is working and they are having their own observatory as well. So they are working from the long time, I guess. And even they are contributing in exoplanet with the NASA as well. They have been like contributed in maybe around more than 10 exoplanet research. Even the universe has disclosed that. So you should just check out that.
and also in TIF and all those research institutions,
Sure.
they have been very limited seats that they might not disclose it publicly like here on internet. But if you just actually go TIFR personally and actually personally ask them, they might have, because my friend is applying for it. Basically, he told me exactly the same.
Where is he? Where is it based on?
He's from London, basically. He's from
London.
UK. Yeah.
Okay.
So he went there for study. He completed his degree. Now he's going for TIFR.
Okay. Thank you,
sir.
Oh, okay. Thank you so much, sir, for coming here. Okay, then that's all about today, everyone. If you still have any doubt, you can just mail us. And thank you so much, Hiten, sir, for your valuable time, and everyone for attending this session. Okay, then. So
sure.
I think that's all. Okay, then. Bye, everyone.